the introduction, and also thank you everybody who is taking time to joining. And I will real quickly share the screen here. And so yes, the talk is not. I saw like this talk. It's they usually concentrate on security. It's not going to fully concentrate on security, but more of cyber physical systems. At the same time, how to bring these the neural networks into the edge devices, like more of a cyber physical system. That is where it's going to focus on. And this is a recycling speech from my PhD dissertation. So I'm not going to cover all of the PhD work and some elements of that, given the time being. And yes, I'm Krishna Muvva, and I got my PhD from University of Nebraska Lincoln, and I co-advised by Dr. Marilyn Wolf and as well as Dr. Santosh Pikla. So you can observe some amazing phenomenon in the nature, right? You can see a falcon chasing its prey only with its eyes without having other numerous sensors, unlike which we see in our unmanned aerial vehicles or uncrewed aerial vehicles, where despite having all these numerous sensors, oftentimes we fail to detect and track our target vehicle or maybe an anti-UAV, which is the interest of us. We can see an amazing phenomenon again with architect turn, which migrate from South Pole to North Pole without using any GPS. But at the same time, it can do this navigation in the miles of this time and also the days in that, like, to do that navigation. On the other hand, we can have challenges with our UAVs, even under canopy, even having a strong GNSS sensors. Oftentimes, it failed to localize where it is, or maybe it failed to perform that SLAM techniques. And we can, of course, see seagulls flying in coordinated path without colliding any other dynamic seagull which is flying with them. But at the same time, we can see some challenges with our UAVs at the same time when they're flying. It might even sometimes get confused with the static obstacles, right? So my research dissertation mainly focuses on how to bring these edge things into there so we can see some phenomena like BARTs. And of course, this is not an easy problem, which you can see as Dr. Minsky at MIT in the times of 1960s. He said that to one of his undergrad students, like, hey, why don't you connect this camera with your computer this summer and solve this vision problem? And of course, we always underestimate that problem, the vision, because we can do this vision very well, and we thought that it is easy to deploy. But up until we're working on this, and we can see like how challenging this could be. And as Dr. Fefeli mentions, that human beings, we tend to take multiples and multiples of images from our inception. We tend to train our neural network, which is our brain, and we are feeding that network so that we are getting better in that. But that is not the case with the neural network. Even if we try, like, for a 10K images, we say like, oh, I did train with the 10K images, why it is not working well, right? But if you look at the human beings, we are being trained for multiple days and multiple years of the time, right? So that is one thing which we can observe. Another thing is, and another aspect is that which we can another see that our brains, which is having a watt power density around 0.5 W, whereas a supercomputer is having a 20 watt power density, which you can see the comparison here that brain can do something, not just can do the task, but at the same time can do an optimized manner. So that is the question we're asking here, like, what can we do that we don't build these networks in a big scale, but can compress this thing and at the same time can put this in the edge devices with a low computer power, right? And of course, this is not just stops with the vision, but we can see even with the controls as well. If you look at the eagles, as Dr. Steve Branton mentions, that they can fly in the low thermals, they can fly even in the turbulent flow. Turbulent flow is a challenging task for us. If you can observe that Navier-Stokes is not solved yet, which means that there is no physics for the turbulent flow, or maybe understanding it, I could put as. So without physics, there is no control. Without control, like, we cannot, anticipate this motion or maybe create a good control input for our vehicle, right? So that is one challenging thing which we can see. And of course, neural networks are very good at approximating the nonlinear functions. So can we provide solutions in that? So this talk mainly is going to be in that lines, like where we're trying to implement the neural networks for perception control, and how we can make these things so that it is not going to be a big neural network with which requires a power hungry devices, but where we can make these things well so that it can be deployable in the edge devices. So that is what we're going to focus on. And so for each of these, I have one parallel in my dissertation, but we may focus on one or two at this point. So learn to track is about chasing a target UAV with a chasing UAV, and we have everything is happening on board with only CPU, not using GPU, to show that we can deploy this on a CPU level of computing. And learn to localize is about cooperative localization between multiple vehicles when the GNSS is not reliable, and at the same time when the environment is not reliable, how we can detect and navigate at the time. And even if the environment is not having a high illumination, how we can still continue the detection. And learn to aware is about the obstacle aware navigation, and which we integrated obstacle aware control obstacle awareness to the control as well. And at the same time, even in the challenging places like where the sensor is not being very well, or maybe the sensor having a challenges in detecting, for instance, a ray finder sensor or a time of flight sensor can fail in detecting in the tree foliage, because the rays might pass us through it. How can we use these lightweight devices at the same time, but yet still able to detect those obstacles even in the presence of ray failures or ray misses? So, but mainly at this point, we might focus on the learn to track first, and given the time, we might go to the learn to localize, and that is the plan for today. So I will just go over a little bit. The preliminaries for us is that the introductions or backgrounds, what kind of equipment we're using. So we are going to mainly using the audio copter firmware for our flights. And we had a co-simulation setup with Mavlink, of course, Mavros, and the AirSim as our graphics engine at this point. And we have a variety of vehicles, which two of the vehicles which we built by ourselves at the lab, and two vehicles which we purchased, which you can see on the left side is the one which we're using the equipment, and the right side is the one which we built it for our custom purposes. And this is one of our co-simulation setup outcomes, which you can see. So basically, I'm just illustrating like the simulation setup is so good that we can transfer the script sim to real very easily. We don't have to change anything in the script. So it is the same script which is working at this point on the simulation side as well as the real vehicle, where we're trying to do an autonomous takeoff and landing. We don't have to change anything. All we have to change is the port. Because of the audio copter firmware and the Mavlink, the Mavros, we connected in such a way that it could be passed very easily. So first we'll start with our learn to track. So as I was saying, the big problem we have with the neural networks is that we have the neural networks, of course, computational intensive, first of all. And we always see a trade-off with this convolution neural networks is that we have a high accuracy networks, which they tend to have a high latency. So they can give a good detection, but at the same time, they take their time, which you can see, like, for instance, if you look at the YOLO model, like you have YOLO Nano to YOLO Extra Large. Extra Large, of course, have a greater MAP, but at the same time, they bring the time constraint there. On the other hand, we have a low latency network, which is something like a Nano or small. They can get the job done much faster. But the problem is that they are not very good, in detecting sometimes, like where you can see two different scenarios here, where the target vehicle is moving in a cluttered environment with a slow speed versus target vehicle is moving in a free space environment, something like a sky with not having much background. By the same time, the target is evasing at the time. You can observe that when the target is evasing and at the same time it is in the open skies, the low latency accuracy network, which can perform well, something like a nano or small, which can, because it can detect very faster and it can give that input to the control, so that way it is catching up. On the other hand, high latency, high accuracy, something like a extra large or large, which is failing. The reason is because it is taking its time to detect, and by the time the target is already out of the field of view. On the other hand, you can see a different story if we look at the cluttered environment, something like where we are having lots of background in the image, something like a trees or maybe buildings or aspects like that. And if the vehicle is moving in the slow speed at the time, so the low latency, low accuracy, something like a nano or small, where it is failing to detect because it is getting confused with all the other feature points in the image, and it could not detect the drone very well. On the other hand, high latency, high accuracy can detect it and follow it very well. So we can see this trade-off of the story here, one element which we're seeing. And second aspect is that oftentimes we think that the neural network has to operate with its full potential or with its full frequency. But that is not the case, which we observed with this target and chasing scenario, and even any kind of a cyber physical system which you can think of, it's doing a job, right? You have a sensor input at the same time when the sensor comes, and you have a control, right? Like as the CPS director says that every time the closing the loop has to be there. You have a sensor and you have control. That's when the loop closure happens. So which means our end product in the CPS is not a vision or not, the neural network outcome. It is the action after that, right? So we have control at this point. So that is where we have a control saturation, which you can see. We have our target vehicle moving at this point, like the same speed and same environment. And we have one neural network and we're changing its frequency, like how fast it is operating. We can see when it is at 0.5 hertz, which means two inferences per 1 second, right? So where you can see that it is not performing well, you can see lots of deviation. Where you have 1 hertz, which means one inference per second, it is performing better than 0.5. But from 5 hertz onwards and up until 10, 15, you don't see much difference at this point. You're seeing the same results. The reason is because even though the perception is acting much faster, but control still needs its time to make an action, right? So that is what it is happening. So there is this no synergy, which means perception doesn't aware what control requires or what frequency control requires, right? So if it knows that value, then it might provide always that particular frequency. And second aspect which you can see is that 10 hertz and 15 hertz may be doing maybe doing the same as the 5 hertz, but at the same time you can see that they're actually consuming lots of computational resources because we're talking at this point on board with the edge devices, which means that they're taking their time and they're using these resources, which is not good, which is detrimental at this point because you're performing the same as a 5 hertz, but at the same time you're taking more resources than a 5 hertz, which is not a good in the sense. That's why oftentimes in the CPS or control we hear the terms like if you're aiming for perfection, it is not so good. Just being good enough is good enough, right? So that is what another phenomenon which we're seeing. So that's when we thought, like, can we integrate this perception and control so that the perception is aware of the controller's requirements and the control is aware of the perception's limitation, so that each can help each other to get the mission successful. So that is what we're focusing on here. So we tend to design a co-design of the perception control. And the first aspect, what we're trying to do is that we have our model predictive control, of course. And in addition to in the cost function, in addition to the control input, and in addition to the error tracking, we wanted to add perception also in the state of the in the co-design of the cost function, so that we can optimize that as well in the resources side, what perception configuration it should use and what type of frequency it should use. Right, so we'll go over with that in a moment. So on the perception side, we picked the YOLO at this point, YOLO V8, which was the state of art then. But of course, after now, like there are so many YOLOs, and of course we have YOLO 20 at this point. So YOLO V8, which was the network which we did use, which was the state of art then, and we have nano to extra large, and we trained on the data sets of 3,000 images. At the time, we have at this point 30K images of this data set. So you can see a trade-off again here, like we have a latency versus accuracy. We have multiple neural networks in the sense. And in the control lab, basically what we're trying to do is that we detect, of course, the target. And after that, we are passing this, we're doing the image to world coordinate conversion, and we're passing that to our control so that it can take the act to follow the target vehicle. And this is overall our MPC in the math equation there. And so this is where we're trying to make our perception control as well, like where the perception is need to be integrated with the control. So what we're doing is that we have our target vehicle, which you can see target could be anything, and we have our escaping distance. So we have our field of view, which means that given the field of view, like which is our the theta horizontal, which we have vertical too, but I'm mainly focusing on horizontal, so it's both are same. So based on this, we can see that if the target vehicle is at d distance and we have escaping distance, which we can get from a trigonometry here. So once we know our escaping distance, we calculating our escaping time. So based on target vehicle anticipation, we see how long we still have until this target is out of the field of view, right? So, and at the same time, we also calculate what perception model which we are using and what is our frequency of operation. So is this is going to operate much higher frequency or much lower frequency? Or do we have enough time so that by the next inference comes, do we have enough time to keep the target still in the field of view, or is it going to escape? So those are the values which we're taking into the constraint here, which you can see what the algorithm here does is that we're taking non true positive, which means it could be a false positive, it could be a false negative, right? So we're taking that, and this is where we're calculating our escaping distance along three axes, which is x-axis and y-axis and z-axis, which means x is front, back, and y is left, right, and z is up and down. So for left, right, which is depends upon, of course, on the horizontal field of view, and vertical, which is depends on the vertical field of view, and this one x, which we assume that after certain time, like as the target is far away from us, even in the field of view, because the vehicle is going to be smaller, so at some point CNNs might not detect well. So that is the distance which we're using there. And we have our non-true positive counter, which we're updating here. And every time we update and we're calculating the escaping time, which means it could be happening any three axis, right? So we're taking the minimum of that. So which means which is happening faster. So we want to concentrate on that. And based on that, whichever model which we are using, this is the model's period time, so how many frequencies it can bring. So that is where we are calculating what are the number of non-true positives which we can have, given that we're still on the game, so we still keep our target in the field of view. So that is what it is happening here, and based on that, we either switch our configuration or we either switch the frequency. So what I mean by switch frequency is that, let's say, if the given neural network is doing a good job, but it is not fast enough in tracking the target, that is when we tend to increase our frequency. And of course, we have a limit for that, right? So, for instance, if a nano neural network, for instance, assume that it can work with, uh, for I'm just giving a number, 30 hedges on a CPU for a sake. So I can go anywhere between 30 and up until, like, below, like, which means I can do 30 inferences per second, or maybe I could do just one inference per second. And of course, I cannot go above 30 because that is the limit for nano there, right? So that is what we are seeing here. Let's say if my large network, if it has only 10 hedges, which means I can go up to 10 or maybe less than 10. So if even if I'm doing good job and if I need more than 10, that's when we see like, okay, we cannot do any much with frequency here. That is when we do the configuration switching. So which means we're switching from extra large to nano, or maybe nano to extra large, given that if we are at the high frequency where we can achieve with that particular model, and at the same time we could not keep the target, that's when we're switching to the low frequency, low accuracy network, so that we can get the high frequency. On the other hand, let's say if we're not doing a good job in detecting, even though it is in the field of view, that is when we go in the opposite direction to get the better perception as possible. So here we're basically switching the neural networks, which we have two different neural networks. We have nano and we have a large. In addition to the error which we're tracking for the target, at the same time, we're also taking this perception to the our control law of our model predictive control, like where we're tracking the frequency and we're tracking the which model which we have, and based on the error and based on the whether we can keep the target in the field of view as it navigates or not. So here are some of the real world results which you can see. Let me just go here real quick. And so here we have we have our target vehicle. Of course, we're doing our detection, and after that, we do the image to old post conversion, and we give the control action. That is what it is happening here. And this is where our situation model predictive control comes and do that action. And here we have a testing, which you can see, like we have model nano acting here, and the background, which you can see lots of cluttering here, and we're going in a normal speed, and that's where we have fails happening when it's enter the tree. And when we do the switching at this point with large. So we in the sense SMPC is doing the switching. And now we cut down here and we go to the clear skies. And when we're erasing, that's when it switched back from large to nano. And so this is a combination, like where we try to do the both episodes in the same time to see how well it can switch. And real world results, this is not the nighttime environment, but simulate we did the gamma correction to the image and do the thing. So this is where our large network is acting here, because we cannot do the switching that fast as we do in the simulation. I mean, switching in the sense from one environment to another environment. So that's where we're doing the gamma correction. So here, when we stop our gamma correction, we feed it as normal, the daylight time and with a clear background. So that's when you can see that it is switching back to the nano. Here we are doing a two-axis motion, and there we're doing one-axis motion, and we prohibit the front-back motion mainly to avoid any kind of potential collisions. So these are the results which you can see, right? We have a nano versus small versus medium versus large versus extra large versus our proposed approach. You can observe that the nano and small are failing when we are in the cluttered background, like when we're in the first setup, like where it is creating so much false positives and maybe false negatives. That's when it could not track well. That is when it is failing to detect. Whereas large and extra large are failing when we switch to a different environment. The switch is shown here with this block line here. And that's when we can see that large and extra large are start failing. And of course, our proposed approach is the one which was able to switch between these networks. That's how we were able to manage and still do the tracking. And this is a computational cost, which is an interesting thing, which you can see that the computational cost is based on how many number of flops which we did, the number of floating point operations, right? We have all the computational costs, like which based on the episode is done. So we're calculating how many flops we use based on the time, how many times the network was run in this operation. You can see that the proposed is the only one which can detect and track well. At the same time, it has the computation cost equivalent to small network. So that is something which is good for the CPS systems or maybe embedded systems in the sense, because we wanted to bring these networks. And at the same time, we want to do the job, but we don't want it to consume lots of computational resources. So that's what the story which you can see that the proposed approach is doing as less as a small network, at the same time can get the job done, whereas the other networks are failing in this point because we don't have a synergy between the perception and control. We have to be aware that the perception is not our end product, because we have our control, that is our end product. So we have to have a certain synergy between the perception and control. And of course, these are the real world results, and which you can see the same story. And this is the computational constraint. So this seems so far so
Uh,
good, right? So that
Krishna, can I
yeah,
quickly come in and
yeah,
ask some questions, right?
yeah, go
So
ahead.
that's fantastic, right? You want to actually incorporate perception and control, and basically the perception is aware of the control capabilities, and the control capabilities are aware of the perception, right?
Yeah,
Now, what is the rate at which these things are operating, right? Because typically a control loop is operating much, much faster than
yeah,
the other loops, right? You also have, I think the MPC is the planner, which you have, and then you have a low level control as well.
yes.
So could you give, firstly, what's the rate at which these things are operating? Are MPC and the perception operating at the same rate?
Yeah, so no, like basically we put everything as a ROS nodes, right? At this point, each one has its own frequency. So we have our perception node, we have our control node. Of course, we have a low-level control, which is coming from the audio captive firmware itself. So there is no like it's not like a perception is control is waiting until the perception comes. Like perception loop operates its own frequency. It's dynamic at this point because given the neural network, given the the YOLO network, let's say I'm just giving a number. Let's say if it operates at 10 hedges on that computer board for a moment, so it could be anywhere between that 0 to 10 hedges, whereas our control loop operates based on the control loop. I believe at this point it is going to operate 30 to 50 hedges. That's where our control, in the sense of motion loop control I'm talking about, but
So
perception
you're
is
saying
done.
the MPC?
I'm sorry.
The MPC is operating at 30 to 50 hertz?
That is correct. And the perception, I mean, I'm talking about the YOLO network output. It is dynamic based on what is the requirement for the given target motion.
Sure. So effectively you have a measurement and then you're going to pass it to the MPC, and the MPC is going to compute this as quickly as possible, independent of how quickly you're getting the measurements, correct?
Yes, we have a stacked state space basically. So that is how it does the measurements.
Right. So once it does not receive, for example, a
Mhm.
measurement, so it will
Mhm.
use the prior measurement, whatever it had.
Yeah, that is correct. So we have a
Okay.
Yeah, we have our perception is not it's not going to come with 50 edges all the time, right? So we have a difference.
Sure.
At the same time,
Yes.
this is the Markov, so which means whatever the previous state, like the present is dependent on the previous state. So there is another Markov assumption I'm going to go over in a moment. So basically, yes.
I see.
Yeah.
Okay, so the other thing what I wanted to ask is in the perception loop, right? When you're switching over between different um, perception modules effectively,
Yeah.
are you using any sort of certificates or guarantees which is coming from the MPC or the low level controller? Because I was expecting that, right? I have a reference trajectory, I have a certificate for that reference trajectory around which I can track, and then effectively using that, I would like to switch.
Yeah. So
Is there some notion of that certificate being used, or is it more geometric in nature?
if I may understand the question correctly, like, so certificate in the sense for the safety guarantee or something like that, or you mean like mainly only the trajectory, whether the trajectory is executed well or not?
Yeah, for example, to make it more concrete, imagine that I have a reference trajectory and then my MPC combined with my low level control can provide a certificate that I will be epsilon away from this reference trajectory for a finite period of time t, right? And
Yeah.
that time t can be like 10 seconds or 5 seconds and so on.
So yeah, basically our reference at this point is nothing but our target vehicle. So the target is
Uh-huh.
goes in a like it goes in a path which is unknown to the chaser. So target like, but of course we do the same pattern like which the metric here is that how far we are from target. At the same time, there is another constraint is that we should not be too close to the target too, because in the x-axis, like which means we're gonna do the collision, right? So the goal here is that we have to be in the same place where the target is along some elements of the x. So which means like, let's say this is my front and back, right? So I have target here and I have chaser here. It need to be here. It should not be here. It should not be here. Or it should not be here like this, but it need to be here as long as it maintains this x safety threshold distance.
Okay, yeah,
That so
that's
that is the
that's
metric
great,
which
right?
we're correcting. Oh, sorry, comparing.
Okay. All right. I'll let you continue. If I have further questions, I'll ping you.
Yeah. So yeah, so far like we're switching these neural networks, which you can see. So it seems like so good so far, right? Like if I talk about this to a control guy, and they might think, oh, that's a good solution, which we're switching, right? But if I talk to a computer vision guy, or maybe a computer architecture guy, they might think like, oh, that might be a terrible solution, right? So they might say like, because we have only two neural networks at this point, and we're doing the switching. But let's say if I want a more configuration, so I might say that, hey, let's bring more neural networks. Let's bring to nano to extra large, and let's do the switching of all these, right? That may not be a good solution, because as you're switching at this point, you have these neural networks are coming from memory to processor and through the cache and going back to the memory if you're not doing those operations. So which means I'm putting lots of computations, even though I'm planning to save this, but at the end of the day, I'm putting lots of computations, right? So this is where we envision, can we do this with one single neural network? Can one single neural network can provide us to be the high latency, high accuracy, at the same time, low latency, low accuracy. So, right. So that is the solution which we want to provide to the question which we ask. So this is where we try to provide an adaptive CNN which can change its configurations, which means it can do an online pruning. So right, so that is what we're trying to do here. If we look at any convolutional network, of course we have nodes, and in those we have filters, right? So there are filters, but at the same time, not all the filters are contributing towards the way we want. Certain filters are learning and they're being useful, and certain filters, of course, are they might do some inferences, but they're not too significant compared to other filters, right? So can we identify those filters, and can we turn off those filters if we do not require? Right? If we can do that, we can have if we are using all the filters at the time, we're going to have high latency, high accuracy. And as we're turning off certain filters, then we can have low latency, low accuracy, right? So that is what we're trying to envision here. In that way, we can give, we can turn off those filters. But how to find that particular filter, right? So this is the metric which we come up with. So our metric has two values here, which you can see that we have mean absolute sum, which is going to tell how important is that filter in extracting the features from the image. And we have a gradient and a backpropagated gradient in the last epoch of the network. We're seeing that it is going to tell that how important is that filter in doing the inference. So this is where we're putting our metric, and of course we're taking this through the some psi value which we're putting, so that we can based on this we observe that which is the best metric here. And we are actually depend more on the features, how much we're getting than this one. I believe at this point we had, when we're doing the testing, we didn't do any online for tuning this value, but for this we have around 0.8 on this side and 0.2 on this side. So which means we're more depend on what is our mean absolute sum of the filter. So with that, we can see that certain nodes or certain filters are not much useful. Then we can turn off those filters and we don't have to use all of those. So here are some of the results from that, which we can see from left to right as we go. Like we have, of course, image on the far left side. And as we go from left to right, we can see that our impact value is increasing, which means that we have a filter which is much needed versus the filter which is not much needed. Like we can see that the left side here, we do not have much features which we're carrying, which are not much useful compared to right side, which you can see. Similarly, like an image here, we have left side. We are not doing anything good in the sense we don't even know where the drone is, right? Because the feature or the feature map is not showing anything here. Versus on the other hand here, we have a certain feature map which is coming here and showing that we have certain level of performance. So this is our impact value threshold results, and this is a visualization with the results as we vary our impact value and seeing how many number of filters it is using versus what is our accuracy and what is our latency, right? So here is a catch, right? To In the beginning, when we do that, we have our accuracy is dropping, but at the same time our latency is not dropping. It is same no matter what. The reason is because the PyTorch or the I'm not sure about PyTorch 2.0 recent version, maybe they did change, but PyTorch first version and as well as TensorFlow. So the way they do the pruning is that they replace those filters with the zeros. So that is the reason why even if you do online pruning, so you can see that accuracy drop, but you don't see that latency drop because the computations are still happening. So there is no performance with the latency there. So that's when we went and we modified the darknet of YOLO, like which is in the C language, right? So we can modify this and we connect our linked list there so that we can do our speculative execution there too. And we can see the latency drop here. This adaptive darknet at this point is in the public domain too if you wanted to use. So this is basically, you give the impact threshold to that and it's going to decide how many filters it is going to use based on the impact threshold. So which means it can give a different level of accuracy versus latency configuration to you because given in the sense here, we're not actually replacing our filters with the zeros. We're actually stopping those filters to do this convolution operation. And so this is our visualization results again with our impact value as it is changing, that we have impact value at 0.0, which means we're using all the filters, all the filters above, all the filters, below 0.0 will get discarded because there is nothing like that. So we're using all the filters, which you can see that detection versus as we go on here. So you can see that it's not detecting all of these things because we dropped certain filters. And of course, we compromising for some accuracy here. At the same time, we're getting some latency here. Latency in the sense we're getting low latency. In the beginning, we put a PID control mainly to do the testing. Can actually it does the performance which it requires or not. So the way we put is that we have two different factors here. We have perception factor and we have latency factor. So the perception factor is, it is going to tell us like whether we're using all the filters or whether we can get the accuracy which we want or not. That is its importance. Whereas latency factor is that it wanted to give as low latency as possible. It is depends upon how much is our error versus where is our target vehicle, where is our chaser vehicle, and how much we are deviating. Based on that, we set up our PID control here. And so this is where our PID activates, like when this is all the control loop which is acting. We have MPC and LQR, which we have lots of controls which we did try. Here at this point, we did the LQR. And you can see that we have our CNN, where we're getting the values, which means it could be a false positive or false negative. At the same time, the error, how it is propagating right from here. And based on that, our PID is going to tell us what is our impact threshold. And based on that, we're going to do our filter activation or deactivation here. So that each time it's going to be in a different accuracy or different latency configuration. So this is the results which you can see that our baseline versus baseline. The way we compare here baseline is that we wanted a low latency, low accuracy network, and we wanted a baseline high latency and high accuracy network. The way we did is that baseline high latency, high accuracy is the same network with all the filters being used, whereas baseline low latency, low accuracy is that same network with only 75% of the filters are used, 20 to 25% of the filters given the network are discarded. Those are fixed at a point. And the proposed, we have a dynamic filter activation and deactivation is happening here. And of course, our target vehicle is moving. And you can observe that, the baseline HL, HA, and LLA are not very good in the tracking the trajectory of the target versus the proposed approach. And here you can see our latency and of course our energy results, which I'll put here. So latency is similar like as we see before as well. And energy consumption, which we identify how much CPU is spending on the energy through the piezo's, the library, and this is the energy consumption, which you can see. Of course, high latency, high accuracy, which is using all the filters, having a more energy consumption. And similarly, as we see previous results as well, we have our proposed method, which has a little lesser energy consumption or maybe a little over consumption equal to the baseline LLLA. At the same time, this is the only method which can do the target tracking well. And so far we have our PID control. So now it is a time to replace that with some good controller, right? So this is where we are taking the Markovian into the story. So you can see that all this error which we formulated, the perception error as a Markovian process, we have one paper on that, which is separately. I'm not going over the math of that. Basically, what is the concept here is that the target vehicle, let us say it is here, right? All the images at this point of continuous for us. So if it is there in the next time step, it is going to be in there. It's not like, teleporting from this location to that location. Wherever it is going in there like that, which means that all the frames are continuous. So that's where we tend to formulate this as a Markovian error, which Markovian process, this entire perception. And you can see, of course, we have our detections and no detections. And no single thing is coming alone in the sense. What I mean is that if we have detections, all the detections are coming in a group manner, not like alone a single detection failure or single detection. Versus if we have failure, again, they're coming in the group manner, right? Assuming you have frames are continuous and at the same time you are in not like taking each frame at 1 second. So the reason why I'm emphasizing on this particular thing is that if they assume that your target vehicle is in the clear skies and it is going to be with that background much of the time and you have going to have good detection, and assume for a moment it enters a zone like where you have background of lots of trees, so it is going to be in that zone for a moment. So in that time, maybe your neural network is not performing well. At the time, it might do the failures. So this is an important piece for us, because if we can foresee that, we can prevent it from happening, which means if it is entering the tree zone, so I wanted to use all of my filters so that I can do the detection well, right? On the other hand, if it is entering a detection zone like a free sky all the time, so maybe I'm going to relax at some point and going to relax certain filters so that I can don't have to use all those filters and I can save some energy. And at the same time, I can do the same detection. So that is what it is happening. That is why we formulated it as it is as that. And of course, we use the TD3, which is twin delight deep deterministic policy gradient. We have our actors and the critic models, which you can see here. And of course, these are lightweight models, which can be deployed on the CPU. And our perception factor, which is the reward, is actually is going to tell us how many active filters which it is used. And it wanted to use all the active filters. Whereas our latency factor is going to see what is our error difference in the Manhattan distance from the target to the chaser. And based on that, it is going to give its negative reward on that. So which means it's going to be like an equilibrium war again here between the perception factor and latency factor. And that is where the training happens. And this is overall our TD3 algorithm. I'm mainly focused on the perception control here. We have motion controller too. So the same phenomenon which we did with the configuration as before, but here instead of that we are having our MDP states, which you can see that our state which contains again the configuration which can tell us how many number of false positives or false negatives which we have, and of course what is our error in the sense with Manhattan distance. And based on that, we're cooking our policy here. What is the best action, which means what is the best impact threshold it should choose so that it can turn off those filters which are not required. At the same time, make our target vehicle move, right? So this is a plot which, this is one of the challenging reinforcement learning controls to try, mainly because the rewards is that if we're doing good for perception, the rewards of the latency are going to be negative. If we're doing good for the latency, the rewards of perception are going to be challenging. So it is in a way like in a way like challenging to train, but we were able to get equilibrium at this point, which you can see that and so this is overall our perception control, like and that things are integrated, and we have as well like a TD3 motion control as well, like which are used here. Mainly, I'm going to show here the perception and MPC or LQR based control results, because I know that CPS folks like to have a safe certification for the control side, right? So that's why we're not using any reinforcement learning control here, and mainly MPC or LQR. And these are the the results in the sense of the Euclidean distance versus where is the target is and where is we are and what is the difference between us. And of course, we did the acceleration comparison to show that which is more reactive, right? If the target vehicle's acceleration is changing, we wanted to show that which is more correlated with that acceleration, whether the proposed base chaser or versus whether the baseline base chaser. So that is what you can see. If we have less dips, which means it is good, which is the case we are seeing with our proposed approach. And of course, again, we have our the competition results as well. Like this is overall in the several trials, and this is our computational resources, which you can see how many number of filters which we have used. And we have 100 percentage versus 70 to 75 to 80 percentage versus, whereas our proposed, which we have varying number of filters, which you can see around 40, sometimes 50, like that. This is overall a summation which you can observe. And finally, I wanted to show these results, like where we have everything is happening in one scenario, like where we start and which is entering in a zone, like where we have evasive maneuvers. At the same time, it is going to in a convoluted background environment, and it is trying to do some maneuvers in there. So we have maneuvers in there. So we have our air sim environment. At the same time, we have done this with our real world test too, with gamma correction of the images, which you can see the HLHA and LLLA and proposed. Where in the zones like we are doing a much faster movements, that's when the HLHA is losing its target because of it could not be quick enough. Whereas LLLA side, it is losing when it is in the cluttered background, because it could not do very good with the detection. Whereas proposed, which you can see that it is at this point not switching, it is turning off or turning on the filters based on what is our requirement. That is how it can able to manage and still attract the target. And overall, these are with different trials which we did, certain trajectories where we made it more evasive, and certain trajectories solely, cluttered background, certain trajectories combination of all of those, which you can see LLA is able to do good when the trajectory is evasive, at the same time it is a clear sky, whereas HLHA can do good where it is in the cluttered background places. Whereas proposed can do, which are like even if you have a combination of all these aspects, which we're still able to do the detection and follow the target. So that is overall I have in the conclusion side. So we started with switching the neural networks in the beginning, and after that we went and modified the darknet of YOLO so that we can get whatever the required latency and accuracy configuration, which we can get we can guarantee that we can get that. And at the same time, we tend to co-design in a way such a way that perception always should know that what is the controller's requirement, as well as the control should be aware of the perception's limitation. So it cannot ask that something which is not possible. I mean, it can ask, but of course, the perception cannot guarantee that thing. So that is overall the conclusion. And of course, I'm at 45 minutes here. So I think probably I'm going to stop. I think if anybody have any questions. And so we have some good, interesting results as well with low elimination too. But you can check our papers too if you're
Hey,
interested. But I think at this point, I'm going to stop here.
Krishna, feel free to highlight some interesting results you really want to share with us. Don't worry.
Oh, yeah, I think, yeah, I could real quickly show this particular result, I think, mainly uh, this one. So this
Hmm.
particular test, I always brag about this test because this was conducted at the low illumination, of course. And this is a field experiment. This is what I'm kind of proud of my results as well. Like at the low illumination condition, and we have actually at the time the temperatures are below freezing. We have less than 0 degrees, and we're getting heated by our car, car heaters, and we're
Oh,
going the
sorry.
and coming back. Yep, yes.
Where is this place? Below
Oh,
zero
this,
degree?
oh, this is in Nebraska, Lincoln, Nebraska, and it's gonna get
Oh,
so cold in the winter times
okay.
and stuff.
Okay.
Yeah.
Good to know
So
that. Okay.
yeah. So basically, the vision can fail in these places, right? And we need to do the localization. That is where we tend to do, again, hidden Markov model-based localization. And of course, we have the LSTM too. And this is the condition where I'm talking about. So I just wanted to particularly show up this result, like where we have a target with, which is very difficult to detect, the UAV, and we still can detect with our proposed approach because we put it as a hidden Markov model and we train the RL there, like which knows where it need to look in that zone versus looking everywhere, and maybe sometimes certain accuracy, certain threshold is not enough, right? So that's where it is failing, whereas this one can go below that and do the detection. And these are the overall results in the comparison where the orange one shows our proposed versus blue is the baseline of YOLO's. We have trained at that time, we have state of art of 11, I believe. We trained until that. But at this point, we have 21. We didn't do the test on that, but you can get the gist of the story. So that's all overall. I think I'll just give a shout out to my group here. So this is a big lab we have here, and my primary advisor, Dr. Wolf, and my secondary advisor, Dr. Santosh Pirla, and and our lab group here. So